Hi, in this presentation I will be showing our most recent results in partially oxidized phosphorene-based sensors and the effect of surface oxidation. I will begin with a short motivation followed by an introduction on field effect devices, pristine and partially oxidized phosphorene, and our computational results on biosensors for nitrogenated species. We all know the importance of detecting and measuring specific molecules in living organisms for different purposes. For instance, these molecules could be indicators of a disease or could help to determine the response to various stresses, effectiveness of treatments, and many others. If we begin from the extraction of some fluid in the organism, its traditional analysis consists on sending these samples to a remote laboratory, which implies high costs and time requirements. The objective of modern biosensors is to enable portable, low-cost, and easy-to-use systems for analyzing the samples on site and avoiding long-time transportation and reading of results, for which smart devices could be employed and diagnosis could be done within minutes. On the left, we have a traditional field effect transistor with an N-type channel. Under this zero bias condition, electron transport through the channel is negligible. However, when we apply a positive gate voltage, we get accumulation of negative charge along the channel, enabling a passage for electron transport. To the right, we see a characteristic IV plot for this device, where we can check that current flux is modulated through our gate voltage. On a field effect-based sensor, we look for current modulation through the absorption of molecules on the channel of the device, having a similar effect to that of a gate voltage, so that different concentrations yield to differentiable changes in the electronic properties of the device, as we see on the figure to the right. By doing so, it is possible to detect and measure target molecules with very high precision and sensitivity. I assume we are already familiar with 2D materials, which are single or few atom thick crystalline structures that have a very high surface to volume ratio. For instance, we can get this wrinkled layer of phosphorus atoms known as phosphorene, which piles up through van der Waals interactions and form black phosphorus. Different to large area graphene, this material is semiconductor. Unfortunately, it has been observed that the pristine structure is unstable under ambient conditions and surface degrades within hours, making it difficult to use in sensing applications. However, there are some manufacturing approaches for improving the system's stability. Then, this work is focused on a recent bottom-up technique that produces few layers of partially oxidized black phosphorus with a 1.19 eV bandgap. Samples were verified to have a significantly improved stability as observed in little variations of oxygen content after 4 months from fabrication. HPS measurements showed that POP and OPO configurations are prevalent, so we started looking at possible morphologies for trying to model this material. Then, we started from pristine phosphorene and used density functional theory calculations for geometry optimization and estimation of electron transport properties. In this approach, we used the generalized gradient approximation or GGA, which underestimates the bandgap of semiconductor materials, as observed in the figure to the right. We then started adding oxygen atoms to the pristine structure and followed the same method for getting a qualitative picture of the system's properties. In addition to the dangling position or T1 that we see in panel B, we also explore bridging configurations as in panel C and D, for which we did not observe a dramatic difference in bandgap energies, although binding energy calculations showed that the dangling position was energetically more favorable, so we continued using this configuration for transport calculations that followed. Here is our field effect device, whose channel is phosphorene with partially oxidized surface. We chose a random distribution of oxygen atoms in the dangling position, covering 4% of the surface area, so that we had available sites for absorbing our molecules as NO, which is a biomarker for asthma in a person's exhaled air. For the electrodes, we use copper atoms for getting metal-like behavior. We then use density functional theory coupled to the non-equilibrium Green's functions for calculating the transport properties of our device, as observed in the green curve. And after that, we added a single molecule of NO, CO, and OH to the surface and repeated the calculations as observed in the black, blue, and red curves respectively. We see that CO has no effect over this bias range, while NO can be detected in the negative range, and its electronic signature is differentiable from other molecules as OH. We then wanted to check the effects of having a much larger coverage of oxygen atoms in the surface, and also correct the underestimation of band gap energy that we obtained with our initial DFT approach. We saw that a much better band gap could be obtained with the density functional theory tight binding approach, or DFTB, particularly using the 3OB's layer cluster parameters, and also at a much lower computational cost. With this, we added oxygen atoms in different concentrations and random distributions up to 50% of surface coverage. With DFT, we saw an initial monotonical increase in the system's bandgap energy that is lower and becomes indirect at larger concentrations, while DFTB shows small variations that are still close to the pristine case. We also studied the electronic contributions from different absorbed molecules on a phosphorene sheet, noting that both NO and NO2 had contributions near the Fermi level, which were observed with both methods. Interestingly, all the other molecules that we studied, including NH3, do not have electronic contributions near the Fermi level, so we focused on NO2 and NO for further transport calculations. These fat band structures and projected density of states figures are presented in the article I cite to the right. For the device calculations, we also use a partially oxidized surface and metal-like electrodes. We observe the black curve for the pristine device and the blue curve for the partially oxidized surface. Then, if we add single NO and NO2 molecules to the partially oxidized channel, we get the green and red curves, showing that both cases have a differentiable electronic signature at these bias conditions. Although these results look promising, we observe that current values are slightly modified when considering a larger coverage of oxygen in the surface. Then, a practical device will require calibration before usage or a very high control of surface concentration during fabrication and its conservation. We have seen that partially oxidized phosphorene could be used for sensing applications of nitrogen-oxygen species, and also other absorbed molecules with electronic contributions near the Fermi level. Also, surface oxidation in the dangling position, or T1, is energetically favored, and concentrations up to 50% show conservation of semiconducting properties, while still having sufficient available sites for binding other small organic molecules. However, we will still require a very high control of surface oxidation for their practical use. This kind of field effect devices could provide some basic architectural nodes for more complex biosensing logic circuits that may be later embedded in mobile devices for a wide range of applications. Finally, our next step is experimental verification, for which we are currently working towards an initial prototype and also exploring other materials that may be easier to obtain and control, and also useful for detecting nitrogenated species.